Welcome to today's welcome to today's class. In today's class, we discuss about the integer programming. So, what is actually the integer programming? Before we start the integer programming, it is very essential to know about the LPP. Integer programming is a special case of LPP. So, LPP means what? Linear programming problem. In linear programming problem, as we know that there are three types of equation. One is decision variable, and if you know the decision variable, with the help of the decision variable, we can create the objective function and the constant equations and the conditional equations. So what is actually your objective function? The objective function consists the decision variable and the parameters. That is minimum z or maximum z equal to c1 x1 plus c2 x2 plus c3 x3 plus c4 x4 dot in this way up to the nth term, that is cn xn. So c1 c2 c3 c4 are the parameters, and x1 x2 x3 x4 up to xn are the decision variables, and subject to constraint. What is actually a constraint? Constraint means the equations are not equal. It is either less than equal to or greater than equal to. That is the inequality equations. So it is a job to convert the inequality equations into equal, and we have to find the feasible solution. According to the conditions, all the decision variables, slack variables, surplus variables must be greater than equal to 0. This is known as a linear programming problem. So we solve the linear programming problem by using graphical method or simplex method. But in today's class, we discuss about the integer programming. What is actually integer programming? Integer programming is a special case of LPP, and we can formulate the LPP, that is known as your integer programming problem, and there are different methods how to solve the integer programming by using same as your graphical method as well as your simplex method. So in this class, we'll learn about what is the importance of the integer programming model, and how to formulate the integer programming problem, and what are the methods we use to solve the integer programming. So, as we know, in linear programming, each decision variable as well as slack and surplus variable is allowed to take any real or fractional value. As we already know, whenever we go to solve the linear programming problem by using the simplest method as well as your graphical method, sometimes we may face that the objective function must be maximized or minimized at a certain point that may be the fractional value or real value. However, there are certain real-time problems in which the fractional value of the decision variable has no significance. Let us consider one example. Suppose I am told that 1.5 men will be working on a project. It is possible 1.5. If you consider the labor, 1.5 labor, 2.5 labor, it is not significance. Or 1.6 machines will be used in a workshop to do a job. That is also not significance. Hence, the integer solution to a problem can, however, be obtained by rounding off the optimum value of the variable to nearest integer value. This approach can be easy in terms of economy of effort, time and cost that might be required to derive an integer solution. So that is the meaning of integer programming. That means the integer programming problem consists of objective function, constant equations, conditions, as well one restrictions, that is all the decision variables must be integer. Must be integer. It is never real numbers or fractional numbers. All such difficulties can be avoided by using integer programming problem. So this is known as your integer linear programming. For example, consider the integer linear programming problem max z equal to 14x1 plus 16x2. That is the objective function as per the LPP. And subject to constant, there are two constant equations, 4x1 plus 3x2 less than equal to 12 and 6x1 plus 8x2 less than equal to 24. And the conditional equations are x1 and x2 both are greater than equal to 0. And the special restrictions are mentioned here, that is all the x1 x2 are integers, that is not fractions. That is the difference between the LPP and integer linear programming problem. By solving it with graphical method, the optimal solution to this problem is x1 equal to 1.71 and x2 equal to 1.71, and the objective function value, that is the maximum or profit, equal to 51.42. So how can you solve this graphical method? Already we know that if we consider the first equation, constant equation 4x1 plus 3x2 less than equal to 12, now we will, let us consider it, that is equal to 12 by putting x2 equal to 0. If I am putting x2 equal to 0, x1 becomes 12 by 4, that is 3. That is 1 point we are getting. Similarly, if we put x1 equal to 0, x2 become 12 by 3, that is minus 4. So if you get the two numbers, 2 points, if you get the 2 points, it is easy to draw a straight line by using the graph paper. So in the first quadrant, you draw that straight line. Similarly, for the second constant equations, 6y plus 8x2 less than equal to 24. Now we convert it into equality. Let us consider 6x1 plus 8x2 equal to 24. If I am putting x2 equal to 0, if I am putting x2 equal to 0, then x1 becomes 24 by 6. That is not your 4. If again I am putting x1 equal to 0, that is x2, that is 24 divided by 8. That is not your 3. If you get the 2 points, again it is easy to draw the straight line by using the graph paper. Now you draw the two straight lines in the graph by using the graph paper. After drawing the straight lines by using the graph paper in the first quadrant, we get a feasible region. With the help of this feasible region, we collect the points, the corner points. We collect the corner points. And by taking the corner points, if I am putting that value in our objective function, z equal to 14x1 plus 16x2, and as per the objective function, where the z is maximized, so hence we get x1 equal to 1.71 and x2 equal to 1.71 and max z equal to 51.42. That is the optimal solution by using the graphical method. So this is actually figure here. If you would draw in this way, that is the optimal solution, optimal point. So there is the feasible region. This solution, as per our integer linear programming, this solution does not satisfy the integer requirements of the variable x1 and x2, because x1 value is 1.71, x2 value is 1.71, it becomes real numbers. So hence It does not satisfy the integer requirements. If we round off this solution, suppose we can round off the solution, that is the distant variable x1 and x2, to become 2 and 2. 1.71, it's approx to 2, and x2 equal to 1.71. Again, we consider that is round off, that is 2. If I'm consider x1 equal to 2 and x2 equal to 2 and putting in the constant equations, that does not satisfy. That means 4 into 2, that is actually 8, plus 3 into 2, that is 6. 8 plus 6, that is not 14. 14 less than equal to 12, it does not satisfy the condition. Again, if I am putting that value in also in the second equation, that does not satisfy the constants. It does not satisfy the constant. Therefore, the solution is infeasible. Therefore, the solution is infeasible. So, there are different methods we can implement to solve the integer linear programming. But before we start the methods, before you go to discuss about the methods, how to solve the integer linear programming, first we know the types of integer linear programming. There are 3 types of integer programming problems or linear programming problems. Linear integer programming problems can be classified into 3 categories. One is your pure or all. Second one is your mixed, and the third one is your 0-1 integer programming problem. So what is this? Actually, pure, mixed, and 0-1. Pure means all the integer programming problems in which all decision variables are restricted to integer value. All decision variables are restricted to integer value. Suppose we know that in integer linear programming, there are 3 types of equations. One is your objective function. Second one is your constant equations, that may be the less than equal to or greater than equal to, and conditional equations. That is then similar to your LPP, linear programming problem. And what is the condition in ILP, integer linear programming problem? That means all the variables, decision variables must be integer, If all the decision variables are integer value, then this is called as your pure or all integer programming problems. Similarly, when some of the decision variables are integer and some of are real or fraction, that is called as a mixed integer programming problem. Mixed integer programming problem. Let us consider one example. Suppose the decision variable are x1, x2, x3. x1 and x2 are integer, but x3 has no restriction. x3 may be real or fraction. At that time, this programming problem is called as your mixed integer programming problem, in which some but not all the decision variables are restricted. Similarly, the third one is your 0-1 integer programming problem. 0-1 integer programming problem means that is the binary integer programming problem. We know that in the binary number system, there are 2 digits, 0 and 1. Here the same meaning here, 0 and 1 integer programming problem, in which all decision variables are restricted to integer value of either 0 or 1. That means if there are number of decision variables, x1, x2, x3, x4, like that, and the decision variables either 0 or 1, either 0 or 1. 0 means executed, 1 means 0 means not executed, 1 means executed. 0 means not happen, 1 means happen. That means that is actually yes or no. That is why your 0-1 integer programming problem. So there are 3 categories of integer programming problem. Let us consider It is a general standard of ILP, integer linear programming problem. In general, the integer programming problem in its standard form can be stated as follows. Maximization z equal to c1 x1 plus c2 x2 plus c3 x3 up to cn xn. So c1, c2, c3 up to scn are the parameters of the decision variable. What are the decision variable? x1, x2, x3 are the decision variable. What are the subject to constraint? The subject to constraints are a11 x1 plus a12 x2 plus a13 x3 plus up to a1n xn equal to b1. Here a equal to 1, 1, a12, a13. So these are the coefficients of x1. Okay, so what happened here? That is the first row. Similarly, in the second row, in second constant equations, we are writing a21 x1 plus a22 x2 plus a23 x3 up to a2n x1 equal to b2. That is not x1, that is xn. Okay. Similarly, am1 x1 plus am2 x2 plus am3 x3 up to am1 xn equal to bm, and x1 x2 xn must be greater than or equal to 0, means positive, and are integer in integer linear program. That is the only restrictions. That is the difference, only difference between the linear programming problem and integer linear programming problem. As we know, what is actually goal programming? In goal programming, there are number of objective functions, but there is no restrictions on the decision variables or slack variables or surplus variables or deviational variables. But in integer programming, there is only one objective function like LPP, and all the decision variables be positive and are integers. Then how to formulate the integer linear programming problems? For example, let us consider a hotel operating 24 hours has the following minimum requirements of the waiters. Period, that is the 1, column 1, that is the 1, column 2, that is 2, that is third column is the period is 3, the fourth column the period is 4, and the fifth column the period is 5, and the sixth column the period is 6. So there are 6 periods, and the time is mentioned, that is 7 a.m. to 11 a.m. for the first period, 11 a.m. to 3 p.m. for second period, 3 p.m. to 7 p.m. for the third period, 7 p.m. to 11 p.m. for the fourth period, 11 p.m. to 3 a.m. for the fifth period, and 3 a.m. to 7 a.m. morning, that is sixth period. So time is mentioned. And the minimum number of waiters required, for the period 1 is 6, for the period 2 that is 12, for the period 3 that is 8, for the period 4 that is 16, for the period 5 that is 5, for the period 6 that is 3. As per the question, a waiter reports to the hotel manager. Generally, the waiters report to the hotel managers every day, day-to-day basis. Manager are the beginning of the period and continue to work for 8 hours. That is actually constants here. A waiter reports to the hotel manager at the beginning of the period and continue to work for the 8 hours. Formulate the problem as an integer programming problem to minimize the total number of waiters required. If you minimize the total number of waiters required, definitely you can maximize the profit. So how to formulate? Let us consider there are 6 periods. We consider the decision variables as x1 for the first period, x2 for the second period, x3 for the third period, x4 for the fourth period, x5 for the fifth period, and x6 for the sixth period. These are the decision variables. That means x1, x2, x3, x4, x5, x6 are the number of vectors required. Minimize, that is the objective function. Minimize, what to minimize? The number of vectors. Minimize z equal to x1 plus x2 plus x3 plus x4 plus x5 plus x6. This is the actually objective function. This is actually the objective function. Then what is the subject to constraint? The subject to constraint is, I am writing here x1 plus x2 greater than or equal to 12. What is the meaning of this? If you start from the period 1, that is x1, and end in the x2, that is in the period 2, the end is the minimum number of vectors. What? I am writing here 12. So that's why I am mentioning x1 plus x2 greater than or equal to 12. Similarly, for period 2 and period 3, I am writing here, you start from period 2 and in period 3, that means x2 plus x3 greater than or equal to 8. And so on, x3 plus x4 greater than or equal to 16. x4 plus x5 greater than or equal to 5. x5 plus x6 greater than or equal to 3. And at the end, look the table here. I am mentioned here 6th period. After 6th period, again you come to the first period, that is x6 plus x1 greater than or equal to 6, where x1, x2, x3, x4, x5, x6 must be positive, that means greater than or equal to 0, and all are integers. So this is an example of pure IPP, means all the decision variables must be integers as well as positive. No fractional or real value are entertained. Similarly, you consider a second example. Second example, a company manufactures 3 products. Let the products are P1, P2, P3. P1, P2, P3. There are 3 products which yield for unit profit rupees 200, rupees 400, rupees 300 respectively. First, again I am repeat here, a company manufactures 3 products, P1, P2, P3, and for the P1, unit profit, per unit profit is rupees 200. For P2, the per unit profit is 400. For P3, per unit profit is rupees 300 respectively. Then each of these products is processed on 3 different machines. There are 3 different machines, machine 1, machine 2, and machine 3. 3 machines are there. All the products are produced. The time required on each machine per unit of the product is given below. In the tabular form it is mentioned. So the first column heading is the product. Then I am below writing P1, these are the product name, P1, P2, P3. And machine 1, machine 2, there are 3 machines I mentioned here, machine 1, machine 2, machine 3. And the machine 1 required the time required per unit, time required to manufacture the product per unit, that is in machine 1 for product 1, 30. In machine 1 for product 2, that is 40. In machine 1 for product 3, that is 20. Similarly, in machine 2 for product 1, that is 20. In machine 2 for product P2, that is 10. Means 10 hours. And again for machine 2 for for product 3, that is 20. In this way, formation 3 for P1, that is 10. Formation 3 for my product 2, that is 30. Formation 3 for product P3, that is 20. And in the last row, it is mentioned as time available per hour. Time available per hour, that is for machine 1 is 600. For machine 2, that is 400. For machine 3, that is 800. How many product of each type? The question asked here, how many product of each type should be produced to maximize profit? That is the job. How to maximize the profit? Fractional units of product P1 and P2 is not allowed. Means the decision variable, whatever we taken for the product 1 and product 2, the fractional value is not allowed. But there is no certain conditions for the product 3. The decision variable, suppose the decision variable we consider x3, there is no restrictions. It may be the fractional or it may be the integer. No issue. So how to formulate? Let us consider there are 3 products. Hence, the decision variables are x1, x2, x3 are 3 decision variables as there are 3 products P1, P2, P3 respectively. What is the objective function? Now we construct the objective function, that is maximize. Because in the question it is mentioned maximize profit. So maximum Z equal to 200 x1. That is it is mentioned in the question, that is rupees 200, rupees 400, rupees 300 respectively L per unit profit. So that's why I'm writing Z equal to 200 x1 plus 400 x2 plus 300 x3. Subject to constraint. Subject to constraint means I am mentioning here 30 x1, 40 x2, 20 x3 less than equal to 600. As per the table, for machine 1, for product P1, 30 hours, for P2, 40 hours, for P3, 20 hours. In this way, what is the total time available? That is 600. So the constant equation becomes 30x1 plus 40x2 plus 20x3 less than equal to 600. Similarly, for machine 2, for product 1, that is 20, for product 2, that is 10, for product 3, that is 20, and the time availability is 400. So the second constant equation is 20x1 plus 10x2 plus 20x3 less than equal to 400. Similarly, we also consider for machine 3, the third machine 3, that is for product 1, it takes 10, for product 2, it takes 30, for product 3, P3, it takes 20, and the time availability is actually per hour is 800. So the third constant equation is 10x1 plus 30x2 plus 20x3 less than equal to 800. And all x1, x2, x3 greater than equal to 0. That's why I mentioned here xi greater than equal to 0. I becomes 1, 2, 3. And x1, x2 are integers. As in the question it is mentioned, fractional units of product P1 and P2 is not allowed. That's why I am writing here x1, x2 are integers because these are the decision variable for product 1 and product 2. x1, x2 are integers and x3 has no restrictions. So it may be the fractional value, it may be a real value. So it is a special kind of integer linear programming. It is an example of mixed IPP because some of are positive and integers and some are positive but fraction or real value. It is a mixed integer programming problem. 4 items are considered for loading on an airplane. So the third example is 4 items. Let us consider A, B, C, D. The 4 items are considered for loading on an airplane which has a capacity of load up to 25 items. That is the limit here. The weight and values of the items are as follows. It is mentioned in the tabular format. Item, there are 4 items A, B, C, D, and weights in tons it is mentioned 2 ton, 7 ton, 5 ton, and 3 ton. And value, that is the quantity per unit, it is mentioned here, that is 10, 36, 25, 14. That is 10, 36, 25, 14. Which items and what quantities should be loaded on the plane? So to maximize the value of the cargo transported, formulate the problem IPP. This is the question. But what is in the question is mentioned? There are 4 items. The weights are given. The value for quantity per unit is also given. But there is restrictions. The capacity to load up to 25 items. So let us consider how to formulate. I'm explaining here. Let x1, x2, x3, x4 are the decision variables for the 4 items A, B, C, D respectively, and that are loaded on the plane. So what is the objective function? Maximize the profit. So that's why max z equal to 10x1 plus 36x2 plus 25x3 plus 14x4. That is mentioned in the question. 10, the value quantity per unit, 36 for item B, 25 for item C, and 14 for item D. That's why max z equal to 10x1 plus 36x2 plus 25x3 plus 14x4. Now, subject to constraint. Subject to constraint means what? The weights, that for item A, that is 2, for item B, that is 7, for item C, that is 5, for item D, that is 3. Hence, subject to constant equation, that is 2x1 plus 7x2 plus 5x3 plus 3x4 less than equal to 25. It is mentioned in the question, that is, which has the capacity to load up to 25 items. So not exceed 25. So that's why I mentioned less than equal to 25, where xi equal to 0 and 0 or 1 means the decision variable that is x1, x2, x3, x4 may be 0 or 1. What do you mean by 0 and 1? That is the binary format, 0 and 1, integer linear programming. So 0 means do not load, 1 means load. If you mention x1 is 0, that means do not load. If x1 is 1, then load. That is the meaning of your 0-1 integer linear programming problem. The above example is known as knapsack problem. What is that knapsack problem? When in an integer programming problem which has only one constant, it is called as your knapsack problem. So methods to solve integer linear programming problem. So till now we know what is actually integer linear programming problem, what are the restrictions, what are the different types of integer linear programming problem. One is your actually pure, means all decision variables are integer, must be integer, and mixed means some are integer and some are real. And the third one is your 0-1 integer, means the decision variable is either 0, happen, not happen, or happen, that is 1, 0 and 1. So there are different methods. Now we come to the point, because we know that whenever you go for round off the decision variable when it is executed as a real value, if you round off, it is also one method to get the optimal solution, but it is not possible. Again, because I am explaining my example. In this example, I am explained already, because in this integer linear programming problem, When we get the optimal solution, z becomes 51.42 at the point x1 equal to 1.71 and s2 equal to 1.71. Here, it does not satisfy the integer requirements. So, if you round off, it does not satisfy the subject to constant equations. So, it is infeasible solution. So, you can round off. Round off method is possible, but for larger problem, it is not used. So, there are different methods. I am mentioning here round off method. It is also called as your enumeration method. Second one is your branch and bound method. And the third one is your Gomori's all integer cutting plane method. So these are the three methods basically we are implemented to solve the integer linear programming problem. So first of all, I am writing here round off method. Round off method. It is also called as enumerations method. Let us consider one example here. I mentioned max z means maximize z, maximize the profit of the objective function, that is mentioned here max z equal to 7x1 plus 6x2. 7x1 plus 6x2 subject to constraint, that is 2x1 plus 3x2 less than equal to 12. 2x1 plus 3x2 less than equal to 12. And the second constant equation, that is 6x1 plus 5x2 less than equal to 30. So two constant equations, one objective function and one conditions. That is, what is the condition? x1 comma x2 greater than equal to 0 means all are positive and integers. Positive and integers. If there are two distant variables, we can solve it by using graphical method. We know in the earlier classes there are two methods to solve the linear programming problem. One is your graphical method, another is your simplest method. If more than distant two variables, if there are number of distant variables, means more than two, we can use the simplest method. Graphical method is not used to find the feasible solution. So in this example, there is one objective function consisting two distant variables x1 and x2, and the subject to constant equation also mentioned, that is 2x1 plus 3x2 less than equal to 12, 6x1 plus 5x2 less than equal to 30, and x1 x2 greater than equal to 0 and integer. Now how to solve? If I am applying the graphical method, it is very easy. Graphical method, applying graphical method, the optimal solution is z equal to 35.5. Z value is 30.55. 35.5, that is maximum. It is mentioned in the objective function. At the point, where is the point? x1 equal to 3.75 and x2 equal to 1.5. So you know that how to solve by using graphical method. First, you take the constant equations 2x1 plus 3x2 less than equal to 12. You convert it into equality equations, that is 2x1 plus 3x2 less than equal to 12 is written as 2x1 plus 3x2 is equal to 12. Now it is required to find at least 2 points to draw a straight line. As we know, to draw a straight line by using a graph paper, we need 2 points. So if I am considering x2 equal to 0, if I am considering x2 equal to 0, then x1 becomes 12 by 2, that is 6. So 1 point, that is 6 comma 0. So you get the first point 6 comma 0. Similarly, if you put x1 equal to 0, then x2 becomes 12 by 3. 12 by 3 means what? That is 4. So what is the second point? That is the second point is 0, 4. By taking these 2 points, you draw a free straight line by using a graph paper, and it is drawn in the first quadrant because both are positives. Similarly, for second constant equations, 6x1 plus 5x2 less than equal to 30. If I am putting x2 equal to 0, x1 becomes 30 by 6, that is 5. The first point is 5, 0. And if I am putting x1 equal to 0, then x2 becomes 30 divided by 5, that is 6. Now we get the 2 points. Now we plot the 2 points on the graph and we draw a straight line. So there are two constant equations, there are two straight lines. By taking the feasible region, the boundary region, and the graphical method, we get the 1 point, that is known as x1 equal to 3.75 and x2 equal to 1.5, where the z is maximum. Where z is maximum. Now, it does not satisfy the integer linear programming problem. Now, by rounding the values x1 equal to 4 and x2 equal to 2, this does not satisfy the feasible solution. This does not satisfy the feasible solution. This could be solved using the enumeration method, but it is generally not possible for large problem. For large problem, it is not implemented. Then enumeration table is used to find the optimal solution of integer linear programming. The rounding solution. If I am rounding the solution, what is x1? 3.75 is just nearest to 4. So if I am rounding the solution, x1 equal to 4 and x2 equal to 1, because x2 is 1.5. So I am downsize that the value of x2, that is 1, and upsize in case of x1, because it is 3.75, it is x1 is 4. Then what do we get? We get the profit equal to 34. The profit equal to 34. So I am mentioning the table. I am taking some values of x1 and the x2 and find the z value that is mentioned in the table. In this table, the first column indicates x1, the second column indicates x2, and the third column is the objective function z equal to 7x1 plus 6x2. Suppose when the x1, I am taking x1 equal to 0 and x2 becomes 0, 1, 2, 3, 4. So for 0, 0, z must be 0. For 0, 1. For 0, 1, z is 6. For 0, 2, z equal to 6 into 2, that is 12, because the first 7x1 always 0. And when x1 equal to 0 and x2 equal to 3, that is 18. 6 into 3 is 18, because 7x1 equal to 0. When x1 equal to 0 and x2 equal to 4, then z becomes 24. So in this way, you calculate the z value, the objective, by using the objective function. Then we consider it is maximized, where it is maximized. Similarly, now we take the case x1 becomes 1 and x2 becomes 0. When x1 becomes 1 and x2 becomes 0, at that time, what is z value? That is 7x1. 6x2 is already 0. So 7x1 means that is 7 into 1, that is 7. And when 1 into 1, that means x1 equal to 1 and x2 equal to 1, at that time, that is 7 plus 6, that is 13. If x1 equal to 1 and x2 equal to 2, then what happens? If you take this value, put in the objective function 7x1 plus 6x2, then you get the z value, that is 19. If you consider x1 equal to 1, x2 equal to 3, and put this value in the objective function, then z equal to 25. So these are the values you consider and put in the objective function. Similarly, if you put x1 equal to 2 and 3 possible conditions for the x2, that is 0, when x2 equal to 0, x1 equal to 2, then we get z function. That means the objective function is optimum value is 14. If x1 equal to 2 and x2 equal to 1, the objective function value is 20. If x1 equal to 2 and the objective function and x2 equal to 2 and x1 equal to 2, the objective function z value is 26. Then we take x1 equal to 3, x2 equal to 0, and we get the optimal value, that is 21. We take x1 equal to 3 and x2 equal to 1, the optimal value is 27. If we take x1 value is 3, x2 value is 2, then the optimal value is 33. Similarly, for another point, let us consider x1 equal to 0 and x2 becomes 0 and 1. When x1 equals 4 and x2 equal to 0, if you put that value in the equation, it becomes, z becomes 28. If x1 equal to 4, x2 equal to 1, then z equal to 7x1 plus 6x2. So that's why we get 34. And when x1 equal to 5, x2 equal to 0, then z equal to 35. I am answering by using a star symbol. It is a special optimal solution. To the previous slide, that is, I am mentioning the rounding solution of x1 equal to 4 and x2 equal to 1. It gives the profit of 34. That is mentioned when x1 equal to 4 and x2 equal to 1, it becomes 34. Then optimal solution to the integer x1 equal to 5 and x2 equal to 0, maximum z equal to 35, means the optimal integer solution is less than the optimal LPB solution. Whatever you get, the z value, and whatever you calculate after rounding off, that must be less than the actual value. That is actually the methods to solve the integer linear programming problem. Methods to solve integer linear programming problem. The second method is known as your branch and bound method. What is the branch and bound method to solve the ILP? Branch and bound method is not a solution technique specifically limited to integer programming problem. It is a solution approach that can be applied to a number of different types of problems. The branch and bound approach is based on the principles that a total set of feasible solutions partitions into smaller subset of solutions. These smaller subset can then be evaluated systematically until the best solution is found. When the branch and bound approach is applied to an integer programming problem, it is used in conjunction with the normal non-integer solution approach. The steps of branch and bound method for determining an optimal integer solution for a maximization model that is less than equal to constants can be summarized as follows. So these are the different steps to solve the integer linear programming problem by using branch and bound method. So what is the first step? The first step is find the optimal solution to the linear programming model with the integer restriction elapsed. The first step is find the optimal solution to the linear programming model with the integer restrictions relaxed. Means in the first step, we do not consider, that means x1, x2, x3, these are the distant variables, are integers. Then second step, at node 1, let the relaxed solution be the upper bound and the rounded down integer solution be the lower bound. So if you whenever you go for rounding of the variables, distant variables, one must upper bound, another must be lower bound. Select the variable with the greatest fractional part for the branching. Create new constants for this variable reflecting the partition's integer value. The result will be a new less than equal to constant or a new greater than equal to constant. That is the third step. What is the fourth step? Create new nodes. One for the greater than equal to constant and one for the less than equal to constant. Then in step 5, solve the relaxed linear programming model with the new constant added at each of these nodes. Then in step 6, the relaxed solution is the upper bound at each node and the existing minimum integer solution is the lower bound. In step 7, if the process produces a feasible integer solution with the greatest upper bound value or any ending node, the optimal integer solutions has been reached. If a feasible integer solution does not emerge branch from the node with the greatest upper bound, then return to step 3. Step 3 means select the variable with the greatest fractional part for the branching. So these are the 8 steps to solve the ILP by using branch and bound method. So the first method we know that enumeration method, that has been the round off method, but that is not applicable for larger problems. And the branch and bound method is applicable to solve the ILP through graphical method. For a minimization model, relaxed solutions are round off and upper and lower bounds are reverse. If in the question the objective function is not maximized, it is mentioned as minimized, at that time relaxed solutions are round off and upper and lower bounds are reverse, just opposite. Then we consider the third method, that is cutting plane method, Gomery's cutting plane method. So there are different steps in the Gomery's cutting plane method. What is the first step? Ignore. That is the third step, Gomery's all integer cutting plane method. So there are different steps. The first step is ignore integer requirement and solve by using simplest method. Here we use the simplest method. Then do all basic variables with integer requirements have integer solution values. If this condition satisfy, then if it is yes, current solution, the required integer LP problem solution. What is the solution you get? That is the appropriate answer, optimal solution. If no, the third step is select the basic variable with the largest fractional value and generate the cutting plane. Generate the cutting plane. Then the next step is you add the cutting plane to the bottom of optimal simplex table and find new optimal solution using dual simplest method. The last method, again, after this, you go back to the second step. If second step is yes, then you get the current solution. If no, again, this process is repeated. This process is repeated till you get the optimal solution. So there are 3 methods: round off method, branch and bound method, Gomery's cutting plane method. The Gomery's cutting plane method is used for the pure case, for the mixed case, integer linear programming problem. Then unimodularity. Unimodularity. What is actually unimodularity? We have noted in the introduction that the general and integer programming model cannot be solved as an linear programming. In the first slide, I have mentioned here. Because if fractional values are obtained in the solution, rounding off may not be possible or desirable. Already I am explaining here. If fractional value is there, we cannot satisfy. you cannot get a appropriate optimal solution. It is worthwhile examining in the context condition if any under which integer programming model can be solved as linear programming yield an integer solution. Existence of each conditions in a problem situation or formulation would make our task simpler as we do not have to apply any new method for solution. The objective of this unimodularity is to examine such conditions. That is the meaning of unimodularity. That means all the decision variables must be greater than or equal to 0 and integers. Again, I am explaining here the cutting plane method. The basic steps of this method is solve a linear programming. To start with, take the linear programming problem with integer restrictions relaxed. So by simple method, that may be we use simplest method or graphical method. If two variables are there, we use graphical method because it is very easy. If more than two variables are there, distant variables are there, we can use the simplest method. Then the second step is check whether the optimal solution is integer. If yes, stop. The resulting solution is the required one. If no, go to step 3. Generate a new constant from the fractional optimal solution of 10, that is 1, of 10 in 1, that is 1, the first condition, the constant is created so as to rule out fractional values of 10 without ruling out any integer solutions to the problem. Then add the constant to the linear programming problem in the first step and go back to step 1. That is the repetition or iteration process till you get the optimal solution. So we know about, again I am summarized of the today's class. In this class we know about what is the importance of integer linear programming. So what is the difference between the integer linear programming and linear programming problem? Only one restriction is there, and there are different types of integer linear programming and the different methods, that is round off method, branch and bound method, Gomery's integer cutting plane method, that is all integer or mixed integer cutting plane method, and how to formulate the integer linear programming as per the, it may be the pure or it may be mixed or it may be 0, 1, because there are 3 categories of integer linear programming. But this integer linear programming is used in the different organizations, particularly in the manufacturing organization, that is not your product mix. Because if you solve this problem by using simplest method or graphical method, sometimes we get the fractional value. That's why we use this integer linear programming method to get the appropriate optimal solution.